Hello, good afternoon, and welcome back. I'm the Internet's Peter Kirn. Welcome to, and I run a website called CDM, which is a Charlie Delta Mango, or Create Digital Music. Since I've had the experience since I started doing that in 2005 of all kinds of people writing me and saying, look at this crazy thing that I've invented. And now over time, this has grown from a small group of people, I think, inventing crazy things, or maybe showing them at academic conferences and stuff, to something that lots and lots of people do. And we have three really, really interesting projects, some of the most cool stuff that you can assemble on stage here for you today in the hallowed halls of East West Studios. So I've got with me on my right Astrid with, I forgot to ask the name of your instrument.
Kepi.
Kepi. So not the Astridophone or the Astrid tube, as I was calling it.
That sounds like something I should have removed.
Oh, no, okay. I'll scratch that idea. On my left is Dan with the, I'm really in trouble. The calicord strum. And then further on my left is Stephanie with the bell controller.
Yeah.
I got that one right.
Straightforward name.
Straightforward name. So we're going to let them show us their instruments, talk about how they built them, then we'll talk a little with one another, and then we'll let them talk to you about why they created these things, and instead of just use something off the shelf or use an already invented instrument, and what that's meant for their music. So first, we'll start with Astrid.
Hi, everybody. The instrument that I'm showing today is actually something that I developed for a study during my PhD, which was, my PhD research was in the Augmented Instruments Lab at Queen Mary. But my PhD was specifically on designing for human error with musical instruments. Because I find a lot of digital musical instruments be like, we all know, you sit it on a table, you don't know what the human's doing, you don't know what the instrument's doing. There's like this, sort of dissonance that is part of this practice. And so what I was trying to do was look at how can we design instruments so the human involvement is more obvious, and that gives like an element of risk. And so for the final study of my PhD, I developed this instrument, and I made 6 of them. Because I thought if I make one, it'll be so easy to reproduce. No. But I did make 6, and they have 3 different behaviors. And the behaviors are, like you see this one, the lights are on constantly. This is just stable. And this one, you need to move it in order to keep it on. Because I wanted to kind of develop this wrist state that required the musician to find a way to play it that kept it moving. And so one of them, it turned itself off quite slowly, and the other one, it turned itself off quite quickly. So these are like come out of a audience study. But the reason I make percussion instruments is just I'm really into percussion. It's my favorite thing to design for. And I wanted to make something that couldn't sit on a table, so that's why it's round, which presented its own problems. And I'll open it up for you so you can see inside. Now, breadboard-alicious, I probably should have neatened this up, but, show me your instruments, I'll look later. I know, my shame. But so what this is actually is a poster tube, because I just wanted it to be a little bit heavy and kind of human-sized, something that you might actually want, like, be able to use in relation to your own body, and which presented its own problems, because underneath each of these are there's a network of piezos, like parallel connected piezo elements that go across underneath each electrode, and I had to figure out a way to kind of form those to the inside of a tube, and you can basically heat it. You can buy a lot of them, because you'll probably screw it up a few times, and you heat it with a lighter and then kind of form it, and there's like an optimal level of heat. And so that's what those are. And the silver bits on the outside are actually capacitive touch electrodes. And what that does is I've separated basically triggering a sample from collecting the velocity data. And the reason for that is that that allows me to have a whole bunch of parallel streams of piezo data that aren't interfered with one another. And so that's kind of how it works. And the ones that tick down also have an accelerometer inside that's heavily filtered in order to reject all of the hit data. So it's got few orders of filtering in order to just detect the quantity of motion. So usually the way that I play it is I kind of toss it around and sort of toss it back and forth, and that's how I hit it. But a week ago, I broke a rib. Yeah, I know. And it's not even a good story. I was walking to work and I fell. And did like one of those, you take 5 or 6 flailing steps and gather a lot of momentum before you land really hard. Yeah, I know, it sucked. So this means that for this very panel, I've had to rethink what I do because I can't really lift it. I can't do the things that I'm supposed to do with it. So I thought that I would show you the way I've been playing it. And of course, because it's got capacitive touch electrodes, which are going bananas at the moment for some reason, that means that you can basically play it with any conductive part of your body. So I thought, well, my feet are also conductive. So I thought, and the one thing that does feel really good is like stretching. So I thought, all right, well, so that's like, what I've been doing is just, this chair's a bit suboptimal, but that's what I've been like kind of playing around with is how do you play it when you can't do what you always do with it? Which is part of what I think is really important about instrument design is this idea of a pluralism of ways to play it, that it doesn't restrict you to only handling it in one way, that the performer can bring a lot of their own style and their own physicality to the way that you use an instrument. So this has kind of been me eating my own dog food because I really have to do it. So the other one that I have here is the same kind of thing. And the way I've been thinking about playing this one is by basically bouncing it on my... And just bouncing it around, so keeping that one rhythm, because it doesn't hurt. And so it doesn't, I don't have to lift it, but I can still kind of do the sort of like stylistic stuff that I like, which is like syncopated rhythms, stuff like that. And I'm also really into drone. So this is, meditative and nice. And so this is like in the last week it's been kind of having to adapt my playing style just to what I can comfortably do. Because I can't do the usual like kind of flipping it back and forth between my hands. So it's been interesting because I've discovered a whole bunch of other ways that I can play it. But yeah, it's exactly the same inside as the other one. This one just has an accelerometer as well that does a quantity of motion. And you can see that when you don't play it enough, the lights start to tick down, and when you have that last bit, there's like a weird distortion effect. It's like when you pull an amplifier out of the wall. And so it's a bit interesting to kind of like think, like, can I keep it in that weird sort of distorty kind of area? And that's just playing with the accelerometer and getting to know that on this like really subtle level. So you've got this like macro thing of how do I interact with it, as well as this kind of more subtle stuff of control. So that's that.
Excellent.
All right.
Yeah, maybe if we have time, we can come back and see, is one of the rest of us able to play this the way that you had originally intended, or they've been adapted?
No, I mean, it does what it does.
Okay, yeah.
So yes, please feel free.
Okay, terrific. Thanks so much. Well, Dan, you have not sustained any injuries, and
there's time.
Not to jinx things,
Yeah.
So no pressure. Let's see if you can show us this without breaking or break a finger, I guess.
Yeah, right, or an instrument for that matter.
Yeah.
Hi, I'm Dan Moses. This is an instrument I like to build instruments and controllers, and this one is called the Calichord strum, which, as the name suggests, is a way to. I'm a keyboardist, and it's a way to offer to keyboardists some of the more rhythmic elements of electric and acoustic guitars. There's plenty of synthesizers that'll let you shred like a lead guitarist, but very few that will kind of let you strum and let you like sit in the pocket and groove. And so that was the impetus behind this particular instrument. Let's see if I can play it. So, yeah, thanks. Thank you. So I love electric music, but I also just love acoustic music, and I love acoustic instruments. And one of the things that I'm sort of obsessed with is finding ways to blur the lines between an acoustic instrument and a digital instrument. And so what I'll sort of explain the very basic makeup. We have 5 tines that are sort of representative of strings, but they have a funny shape. And each one has a pickup on it. And the funny shape allows it to be a piece of acoustic material. So you can pluck it in all sorts of different ways. And it's really sensitive, and depending on where you wear, it has its own acoustic properties that will excite the other half of the instrument, which is some physical models that are sitting inside the the body, running on a belloboard, actually.
I didn't even mention that.
Astrid basically makes the belloboard.
No, I'm part of a team that developed the belloboard.
She all by herself. And,
Hammer resistors out of metal in it.
Exactly.
Yeah.
So, as a keyboardist, if you play notes on the keyboard, those will set the pitch and some various other parameters of the physical models. I got a few different sounds in there. I got a nylon string guitar and an electric guitar. This one's fun. But one of the things that I found very intuitive, that is a lot of fun, is the fact that when you're holding notes down, you get a chord and it sustains. When you let go, it damps, but it's not off. Right? It's basically still modeled as though you've just like kind of like put your hand on the strings, right? So that's what guitarists do, right? You hit the strings hard and you dampen them at the same time to effectively have an extra percussion instrument at your disposal, and that's how you get this like sort of a rhythmic effect, which is a lot of fun. I threw the key bed. So you can play it with MIDI input. You can also I created a keyboard made of nails that are capacitive, touch sensitive, because in this instrument I'm not using velocity information from the notes at all. I'm just using note on and note off. So capacitive touch makes a lot of sense. And just for fun, I created 2 keyboards, sort of filleted them out for some various purposes. The most simple of which is it's just an extra octave down. Or, if you're so inclined, I have a chord mode. So that's handy. And then if you disrupt the chord with a note on the top keyboard, you can turn a major to minor, and it'll be sticky, which can be useful for setting a chord progression or something like that. I can undo it with these presets down here. And probably one of the things that has been fun is just sort of like throwing features into this thing. It's what's great about making your own instrument. You can just be like, what if it does this? What if it does that? And so this is, in many ways, you make these things and then it's a prototyping platform. So one feature that I found especially useful is I actually put a looping pedal. It's not a pedal at all. But I put a looper in between the 2 halves of the instrument. So you can actually loop just the strumming half and then play the notes afterwards, which is really, really useful. So if you like, if you just loop the strum like this, that sucked. I'm going to do that again. We're all familiar with this game, huh? Slow it down. There we go. So, a guitarist is doing these things in real time. You're doing both things simultaneously, but you don't have to. You can focus on just playing the notes or just doing the strumming. And if you do it this way, then your hand is, woo, that's loud. Your hand is freed up to play other instruments. So if you have a keyboard and you want to play a bass line, right, so you can really, thank you. Yeah, and it's a physical model. You can do all sorts of fun things. You can, ooh, I need to turn it back up. The electric guitar is unfortunately way louder than the other instruments. You can palm mute with a knob. Which is especially useful for kind of groove guitar. So, how are we on time? Good?
You're good. You keep saying the words physical model. What's a physical model?
What is a physical model? It's literally modeling the physics of an instrument.
It's a model of something physical.
It's a model of something physical. It's a type of sound synthesis where instead of working with sine waves in a particular way, you're literally like concocting concocting a DSP version of an instrument. So it behaves. You sort of give it all the physical parameters, and it plays like a real instrument. The main difference between sort of the typical way to do physical models is in the excitation. That's really the big difference here. Typically, physical models, especially of string instruments, are a pretty long studied tradition. But they're usually played with a keyboard, and they're usually like you hit the keyboard and velocity turns into some excitation signal, which is great and can be really expressive and really fun to play with parameters. But I like to strum things, and I like to hit things, and I like the way it feels, and I like the unexpected results when you play something in a way that it actually hadn't been designed for. And so using acoustic materials to excite these models is really just kind of opens up a mode of expressiveness.
Well, and actually, people here, live users can play with some of these sort of models in my brain. What are the live instruments called that do physical modeling? Audience participation, Fran? Corpus.
Yeah.
Tension and collision. Collision being my personal favorite, but yeah. So those things are there if you want.
They're there. They exist. You can play with them. It's a lot of fun. I highly recommend making weirdly shaped objects and seeing how they sound.
Yeah, fantastic. But you have something else under your table. I think we have a minute. Yeah,
right.
If you want to show that.
1 minute. This is the original Calicord. I'm referring to it as the Calicord family of instruments. They all sort of use this this concept of sort of blurring the lines between physical models and digital instruments. So this one, the tines are very rudimentary. They're actually just little piezo film. And you can just strum them. And then on the right-hand side, kind of like an accordion, there's buttons that you can play bass lines with. And the bass, your thumb can control what the bass notes are, and everything else is just 5, 1, 7, or whatever. But when you play a tonic with your thumb, it changes the chords of the piezo instruments. So you can do things like this. The buttons are very small, yeah. And you can rotate the thing for extra range or for various other effects, like wah-wah, things like that. So that's the calicoid. Okay.
Thanks so much. Well, so for our last presentation, we have something a bit different. This is a piece that can also work sort of as an installation, and I'll let Stephanie explain to us why there's this big metal thing with a ton of bells attached to it.
Yeah, exactly. So I'm here to talk about the bell controller, but I did want to give a little bit of background information on kind of why I started working on stuff like this, and I think it'll give you more insight as to why it's taken this kind of Frankenstein form. So I have some slides that I'm going to show you. There we go. So a long time ago, maybe like 10 years ago, I started working on installations, and that was kind of what I was interested in doing. And in one particular one, I wanted to create the effect of having kind of crickets in this very large room and kind of evoke the night-calling insects. And that was just one aspect of this installation. And so to do that, I found junk metal. These are actually heat sinks that I got from Apex Electronics. They have a lot of like junk metal there. And resting on top of each one is a vibration motor that has a nut around it. And so when it vibrates, it's activating the heat sinks. And when I was working on the installation, I found that actually I preferred just performing with the crickets. So I kind of scavenged them from that project and started performing with them as an instrument. And you can see here, it still reeks of like installation-ness. It has super long cables, like everything's kind of modular, so I could spread it out around the room. But this is kind of where my interest in doing this started. But back then, the only thing I could do was just turn them on or off, and that was it. And then if they were on, they would do some kind of repetitive vibration pattern. So then, not too long after that, I worked on another installation. This is a picture of it, and this is where the new acoustic object that you see here kind of entered the picture. So the way these work is all of the sound that you'll be hearing is mechanically generated from this object. So it's a vibration motor, that's this here, with a nut, just like in the older work that I did. But hanging off of each one is this jingle bell or sleigh bell. And I've prepared them each so they're kind of muted with a piece of tape. And then wired in parallel is an LED. So anytime it vibrates, it also lights up. And it also corresponds to the intensity of the vibration. So again, when I was working on this project, I found that I preferred performing with it instead of installing it. So I decided to just bite the bullet and design a controller that would be more convenient to perform with and have some more expressive control. So I started prototyping this. I'm using an Arduino Mega, started soldering everything, putting it together, kind of made an improvised design. As I was building it, I decided how I would arrange things. And the end result is this. So you can see there's a series of switches here, and the mouse is hard to see over that. But each switch controls a bell, and that basically what it does is it turns on the bell. That's nothing new. But what I added, so let me turn on a bell here. Oh, and you know what? I need to power it up. Okay. Okay, so let me turn on a bell. So here's one bell. It's currently looping, just turning on and off at a set time. So these knobs here that I added control things like note on length, note off length, and then intensity. So this first one on the left is note on length. So if I make it really short, this is as short as it can go. And then if I make it really long, that's as long as that can go. I'll go back to somewhere in the middle for the demo. Note off length is the second knob, so that's the time that's the rest time. So again, I can make it really short. And I can make it long by turning the knob all the way up. Really long. Okay, back in the middle. And the last knob is intensity. So this, right now it's kind of midway. If I turn it up, it should get louder and brighter. So that's the highest intensity. And then I can turn it down. And there's a nice in-between here where if I turn it down just right, the LED will still light up, but it won't be enough to power the motor. So I use this a lot when I'm performing, kind of like a lighting effect. I'll fade them in visually and then fade them in sonically. And of course, I have many of them. So let me turn them on. And I guess I'll turn on the big ones too. I also added another control where it's this thing here. It's kind of awkward because I kind of improvised adding it on. It's a force-sensitive resistor, so all it's measuring is how hard I'm pressing on it. And I have two modes. One where if I press on it, it'll speed things up. So now it's as fast as it can go. And then another mode where if I press on it, it'll slow things down. It's pretty sensitive. I could tweak it, I guess. And when I started performing with this, it was always acoustic. I wasn't miking it or anything, and that was great for small audiences, small rooms. But there were times when I really wish I could make it a little louder, maybe amplify it. So I started doing that. That's the version that you see here now. So I've got I'm just miking it with two condenser mics, but another part of it is I started using this hollow metal stand, and there are two contact mics attached to it. So they're picking up the vibrations that's passing through these contact points. So if I turn, that's this one here.
Yeah.
And I've EQ'd them a little differently. So this one, and then usually when I'm performing with this, I'll do live mixing, and then maybe, I'll cut out completely the condenser mics and do something more focused on the amplified sounds. And then last but not least, let me go back to, oops, sorry about that. Last but not least, so this whole thing started from an installation, and so I wanted to keep part of that, I wanted to keep that element with it. And so there are two modes for this whole controller here. There's performance mode, which is what we're in right now, where everything responds directly to what I'm doing. But then I have an installation mode, which we're in now. An installation mode essentially means that each motor will come to a point where it's going to decide whether it will sustain a tone like this, do a regular blip like these are all doing, or stay silent for a long time. And so each of them are doing that at different rates. And having 15 of these do that kind of gives an illusion that they're maybe interacting with each other, maybe conversing with each other. I definitely think of these things as creatures, by the way. So I use installation mode too in my performances. It's not just if I want to install it somewhere, which I actually don't really do anymore. I mostly perform. So that might start something like this. So that's very short. Thanks. And one thing I like about this is when just the light's going and the motor's not, you can still kind of hear the motor try to go. And so that's what that thing is at the very end that you heard. It's very quiet, but it has kind of a nice effect. But yeah, that's...
Can you turn that up for us a little bit more?
Yeah, sure. Yeah, it is very sensitive to feedback is one thing about this whole thing. Yeah.
Excellent. That's probably the softest noise you'll hear this weekend.
Yeah.
Yeah.
Thanks.
Cool. Yeah, well, thanks to all three of you. Let's talk a little bit about this. Of course, so we're talking about physical digital hybrid instruments. So I wanted to ask a little bit about the brains, the computation inside of these, which I think means talking to you. So you're on this team that's developed Bella, which is what's powering your instrument and Dan's as well. What is Bella?
Bella's a hardware platform for ultra-low latency sensor and audio processing. And it was developed within a research group at a university, directly in response to issues of latency within action to sound. And there's two things there. There's the actual latency of like how long does it take for your action to be processed by the system and result in a sound. And when you start working with Arduino, especially if you're doing action to sound stuff, if anyone's ever done it, you know there's like an event horizon where all of a sudden you can't, it just doesn't, it's not responsive, it's too latent, because the latency can be quite dramatic, especially if you're trying to do things with, for example, plugging something into a laptop when it's going through an OS. Doing any of that processing can gather a lot of latency where action to sound becomes really problematic. So what Bella does is it runs on a BeagleBone Black, which is a single board Linux computer. And the special sauce there is this library called ZMI, which is, it basically pushes all system processes to lower priority than the audio thread, and therefore the audio is always processed first. And so that it addresses latency there, where it just is, you know, a clever way of dealing with only one core in the board. But more than that, there's also this issue of jitter, which I think is an even more dramatic thing that is talked about less. And jitter is an irregular amount of latency. So you might have 50 milliseconds, you have 152 milliseconds, and you have 4 milliseconds. And it's that jitter that actually makes things feel clunky. And the way that Bella is designed to address that is that the analog sensors are sampled at exactly half audio rate. So every second audio sample, the analog sensors are also being sampled, the 16-bit, 8 16-bit audio inputs, analog inputs. And because those are at exactly half audio rate, that means that the audio thread and the analog data are chained very tightly together. And when you, with an Arduino, the Arduino just, you know, samples the analog pins whenever it has time, like whenever it can. Right. And so depending on the stress that is happening on the system, could be any time, who knows? And so that was a lot of our research was on optimal levels of latency and how to address this, and does it matter? And we found that jitter matters a lot. And so that was one way that this is specifically designed to address that.
So if you open this up again, I think we'll see the Bella board in there, right?
You mean take the tape off?
Yeah. Sorry. We'll see the board in there, because this is it's also not an expensive thing, right? This is, I forget what Bella's costing these days. If you have the Bella and the Beagle together.
Yeah, this is don't look at this one, because this is a really early prototype that I found, that I managed to put in the instrument. So our connectors are no longer the color of a foot, but they're now white. But it's basically the same form factor.
I didn't give them enough warning, because we don't actually have a camera on you, but.
That's okay, it's right here.
It's a little board. It's smaller than the size of your hand, yeah.
And we also now have a Bella Mini, which is 1/3 the size, which is very, very small. The difference between the Bella Mini and the original Bella is that the original Bella is onboard speaker amps, which you can run speakers by powering with a 5-volt connection to a mobile phone battery, for example. And the Bella Mini also doesn't have analog outs. It's only got analog ins. So, because we found that people didn't necessarily want those things. They wanted things to be really small. So we just got rid of everything that we thought we could afford to get rid of in order to make it smaller. So that the Bella Mini is teeny tiny. And that runs on top of a Pocket Beagle. And whereas this one is with a BeagleBone Black.
But these are all costing about it's like $100 or something. Right?
It's about I think it's 155 pounds for the original Bella, and the Bella Mini is, I believe, 130. Okay. But the exchange rate is certainly advantageous to Americans right now.
Tell us what that means for your instrument, Dan. That's kind of inside there. That's the digital brains. And because you have computers hidden under the table. Sorry. You have nothing hidden under the table.
The computers under the table are actually, because of that last instrument I played, the original Calicord is running on Max MSP on my laptop down here, and that's like one of the most exciting things. I mean, Bella's amazing for a lot of reasons, and one important one is that you can build finally a self-contained instrument. So I haven't had time to do this, but the next round of the regular Calicord is going to just have a power and an audio jack, and that's all. I won't have to hook up to a computer and an interface and all this other stuff, which makes it so much more of an instrument. and so much more of a, I mean, it helps with travel time, but it also just feels different to like have a piece of hardware that does something on its own without connecting to anything else. We were just talking about this about guitar pedals earlier, how it's like there's something magical about a guitar pedal, even if you can have a like multi-effects unit on your computer. There's something about this physical object that sits there and does its thing by itself that's, I think, very compelling musically and sort of creatively.
Yeah, and it also allows you to use an instrument in a very kind of musician-y way.
Yeah.
I mean, one of the reasons I love percussion, especially drum kits, is that the drum kit isn't an instrument. It's just a collection of parts that are connected by your reach. And so it can be anything. And that's one thing that I really love about embeddable systems, is that it allows you to use it in the context of your body. I mean, that's what I love about percussion, is that, like, you know, every kit is a little bit different. The heights are really specific because that has to be tuned to the performer and their style and their reach. And with digital instruments, it's something that I was always really missing, when you have to like have a really long lead and then push the laptop off stage.
Well, so to be clear, this thing can operate without the computer, and the reason right, the reason that these boards are able to do this is partly because we have this sort of scale of manufacturing now. The chips that are inside your tablets and phones. There's something with the kind of similar architecture on the Bella. Actually, I don't know which chip is on the Bella now.
The current Beagle, the Pocket Beagle, uses an Octavo chip.
Okay. So these are the same kind of architecture, roughly, as what's in your iPhone or your Android phone.
They're
or
ARM
an iPad.
processors, yes.
Yeah.
Yes.
So, but to kind of probably, how many people here have used an Arduino before? Somewhat. Wow, okay. This is not an average sample of the population. Slightly self-selecting, but so we don't have to explain what an Arduino is. But what in your case, the Arduino is the only computation in your setup, right?
Right. So I decided for. I guess I don't really enjoy performing with a laptop. If I do, I try to push it to the side or something. So for this, I wanted to just eliminate the laptop. And so the Arduino is where all the logic is. And I guess I have a slide if I could get that up there. There you go, there it is underneath all this stuff. But here's just like one excerpt of the code that's on it. So you might have noticed that when they're all going, none of them are actually ever lining up with each other. They're all kind of going at slightly different rates. But what's happening in the code is they're all using the same function. It's a motor control function that I wrote. And that's where all the logic is, where it reads the knobs, the switches, and everything to tell the motors what to do. But the part that's different between all of them, and they're in the form of variables here, is this T0 and T0 rest. And so that's kind of the base unit of the note on length and the note off length. And they're all slightly different. And I did that manually. I just hard-coded in different base units for each one. And so they're all off by like maybe 20 milliseconds or something like that. So, I don't have it up here right now, but if you are interested, the code is on GitHub. But it really is just a sequence of conditionals. I can't even recite it from my brain right now. But I guess my point is the logic in all of this is very, very simple. It's just a series of decision making. And I would say probably super lo-fi, no Bella board or any amplifier or anything like that. So.
Well, but worth saying that both these projects make pretty heavy use of the piezo microphones, right? So.
Yeah.
There's a lot that each of these projects are getting out of the sort of physical part. Mm-hmm. There's a lot that both these projects are getting out of the microphone, right? Mm-hmm. So there's just a lot of the complexity is actually just coming from the sound, and like this is beautiful what's happening with the vibrations through this frame, and we were both smiling. Yeah. We were both enjoying the frame vibrations. Yeah.
Nice.
So even if that kind of motor control part is simple.
Yeah.
So actually, I guess that's a question for all three of you. Are you all three sharing stuff on GitHub? Can we find? Is there some documentation of your projects that we can go look at, or we can look at your motor control code, or experiment with it on the Arduino?
Yeah, for sure. You can rebuild it.
Where do we find that for any of the?
On GitHub, I'm Steffi's Castle. If you can remember that, yeah. And it's called Bell Controller, and you'll see some other projects on there if you're curious. But I do post my code on GitHub when I've finished a project, yeah.
Yeah. I mean, I know a lot of us write code that we really don't want
I was
anyone
going to
to
say,
see.
exactly
I
what I
don't
was
want to
gonna
tell
say,
you my
like,
GitHub name because then you'll see how shonky it is. Don't know.
It's very hacky.
Just forget that it's you. Yeah. Okay. So we don't want to say. I don't know. Are you sharing anything?
I don't have it. I don't even have a GitHub account, so it's.
Well, that was another thing all of us were
Wow.
talking about, right? That none of us had an engineering background, right? So none of you all had originally come from engineering. What was your background, and where did you get from your sort of artistic background to thinking, oh, I should start building something? Was there sort of a learning experience that you had, or you had a teacher, or you saw a performance, or where did you come from, and how did you wind up getting here? I guess actually starting with you in Shonky code.
Yeah. Yes.
Shonky.
Well, I mean, it's
We're
all written
shonky
under
code, you know.
duress. My first degree was in sculpture and performance art.
Okay.
I went to art school after planning on being a concert pianist, trained my whole life for that, and then realized, no, I can't do it, and ended up going to art school as a last resort. And I have a master's in public art and public sculpture. And I worked for over a decade as an installation artist, always doing a lot of things with computers and sound, but never had access to this kind of engineering. And then when I ended up in a PhD program, that I was like, okay, I really want to learn the physical aspects of computing. I really want to be able to learn electronics properly. And the best person happened to be in the Augmented Instruments Lab, Andrew McPherson, who's amazing. And so I was lucky enough to convince him to take me on, even though he really shouldn't have. And that is it was kind of nice for me to close that loop of both art and music. And that was, I think has been a really important transition for me.
But you draw on that sculpture background too.
Absolutely, because I think the physicality of instruments is really, really important. And also materials. I mean, we talk about, what it means to use piezo sensors. I mean, this is a poster tube. I made these out of poster tubes. But that's because the cardboard has a certain damping quality that's really, really nice. And this tape around the LEDs, this took me forever to find the right tape. This is tape that you use to tape up broken ankles. And because it's so thin, it's not conductive, so I can hold it here and it won't trigger the electrodes. And it's really thin and it doesn't disrupt the so I think materials are absolutely important. That's completely from my sculpture background. It's just being obsessed with the physical world.
Yeah, this is why it's so great to bring different skills together. So I don't actually know what your background is either.
I actually do have an engineering background, but in a very weird circuitous route. I don't want to bore people with the details, but basically I got my undergrad degree in engineering, and then I said...
What kind of engineering?
That was mechanical.
Mechanical engineering.
Yeah,
okay.
A long, long time ago, and decided that was the only thing I knew coming out of college is I didn't want to do that. So I was playing a lot of music, and I actually decided, well, maybe I'll see if I can study music. So I went and got a master's in music, and was just a jazz musician. Trying to make my way, and had a day job writing code because that's how you pay the bills when you're a jazz musician, or if you don't want to teach, at least. Then I thought, well, may as well, as long as I'm writing code, I may as well, get decent at it. So then I got another master's degree in double E, and that's where I was studying. I was at Karma, and.
This is at
Stanford. At Stanford, yeah. I got a double E at Stanford, and that was sort of where the worlds finally started to interlock, and we especially learning about physical models, and I was it just blew the back of my head open, what was possible and what was still yet possible to make, and ever since then I tinker as much as I possibly can because I just think it's an exciting world. There's a lot of instruments. I feel like this is lagging. I feel like software is so well developed right now, but interfaces are not. And part of that is just the nature of commercial and how expensive it is to manufacture physical things and take a big risk on, and then if people don't like it, then your company goes under.
Oh yeah, every single knob.
Right.
Yeah.
Right. So there's reasons for it, but if you're a hobbyist and you don't worry about investors, there's like so much potential in physical interaction that is, I think, right now untapped.
And Stephanie, you also came from some art background, right?
Yeah, I went to college and studied music in college, and then I got a master's degree at CalArts, actually, not far from here, in experimental sound practices. And that was really when I first started kind of combining like programming with physical objects and musical experimentation. But as a hobby growing up, I was doing web development, but not an engineering background. It was all everything here, and what I know about web development is all DIY. I learned it on my own, maybe not like that polished, but I really enjoyed being able to combine what I knew with programming with something musical. And so that's, I guess when I was getting my master's degree, that's when I started combining them finally.
So we have a kind of a frightening amount of academic experience probably assembled on the stage. But I mean, kind of looking at the community, which is nothing against that, but I think looking at the sort of scene for these sort of DIY things on a broader scale, people have all kinds of different backgrounds, and some of them have no master's degrees.
Really all the, actually, I don't know if I should say this, but all it really did was it pointed me in the right direction on the internet to find tutorials to teach myself how to do things.
So the winning university and all of this, both in terms of cost and knowledge accessibility, is the internet. But that's nice to hear, since we've mostly been hearing lately about the bad things, the bad ideas that the internet is spreading. The internet is also spreading ways of making cool musical instruments, and not just crypto-fascism things. But, so it's good to hear there's a good side to it. Well, let's hear from the audience, actually. I don't know if we have a microphone running around, or I can also repeat what you're saying pretty easily. Yeah, sure.
I've actually been thinking of building something very similar to the Calicord, kind of inspired by something I saw at NIME on the Bela team. I actually ran into Astrid there, and I accidentally broke one of her tubes. But anyway, so
not her rib though.
I am very sorry.
It's okay.
So what I'm wondering about is how did you mic those flex fake strings sort of thing?
How did I mic them?
Yeah, where do you put the piezo?
I glued it.
But it's attached to the actual membrane.
It's attached to the membrane, and then one of the keys is that where it's held, you just got to make sure that the piezo is at that juncture, because that's where most of the energy is.
All right.
Yeah.
All right.
And you kind of played around with it and experimented to find the right spot.
Absolutely. Yeah. I mean, if there's one catch-all piece of advice, it's iteration, iteration, iteration. Just keep you try it and try again and listen, and trust yourself and be creative and try new things.
Cool.
I guess I was thinking about the idea of boundary value, modeling of sound problem type situations, which could be slightly different based on all three of your instruments, but it would still be applicable. So I guess I was mostly thinking about the shape of the shark fins on your guitar thing, and about if you modeled those before you cut them, and if they, for example, on a string gauge, trying to maybe if you were working on trying to mimic string gauge with modeling the shape, or if it was trial and error. And I was also thinking of a similar or an analogous question about how I noticed that when your crickets were starting to, they were all kind of spread out, a little bit less percussively dense, and then they all started to see your system started to excite, and they all started one by one. They all started to become more fast and more rapid in their movements, and then it just kind of reached a chaotic point and stayed there. So I guess those were two separate questions, but related to modeling of chaos in systems that I was wondering about.
Chaos in systems and how shape influences your work. It sounds like,
I mean, speaking from my process, it was entirely trial and error. One of the things that's neat about doing modeling that way, the way that you're describing, is the ability to let the computer help you with the trial and error. But at the same, it's kind of still trial and error. I cut out a bazillion different shapes, a bazillion different thicknesses, a bazillion different. That's a technical number, bazillion.
Is that metric?
Yeah, a ton of like thicknesses, materials. I tried coating them in things. I tried laminating different, microphone material. Like I just kind of like listen and then listen and play and try again and like. But one of the things that kind of helped was getting to a point where I sort of had a mechanism where it's like cutting out a new thing and putting it in and wiring it up was fairly quick to be able to hear it. But yeah, it was all just like trial and error.
And Stephanie, that was sort of a similar experience for you?
Yeah, so when I was building this, I didn't really know yet how to perform with it. I just built in ways to change different aspects of what the motors were doing. And then I added in like this installation mode. And so that installation mode, I think, is when it first started. Things were really spaced out. But as I was performing with it, I would change some settings. And I eventually, after performing with this quite a bit, I found a way to smoothly transition between what seems like very spaced out slow stuff to go into what I know as performance mode. And so I guess what I'm trying to say is also same experience of trial and error, but it's more like I had to learn how to play the instrument that I built. I think the chaos aspect of it is actually very controlled chaos that I am directly affecting.
I didn't know if that was the automated mode that you were using at that time, or if you were playing the instrument at that time.
Yeah, so it was a combination. Cool. Yeah, so it's kind of transitioning the automated mode into the performance mode.
Let's take one more question, and then we'll, sure, up in the back. We'll keep talking after the session is done.
I just want to say amazing instruments. How do you think about the separation between the time that you spend designing the instrument versus the time that you spend learning how to play it? Because it can be so tempting to always like, I'll just add one more thing, but then you never actually learn how to play your instrument.
I think that these instruments were developed, as I said, for this study, where I had six percussionists playing, like one percussionist playing each instrument. So I was actually designing as a percussionist with like what I thought it needed, but also having to make it not this like completely idiosyncratic thing so other people could play it. And that was I'd never done that before. That was a really interesting process. Mm-hmm. And it was also fascinating, and I don't know if any of us I'd never had this experience before. Giving it to six percussionists and seeing what they did with it was amazing. And that really was also invaluable feedback of, this kind of pluralistic methods of playing an instrument, which is really important to me. Was that present? Yeah, it was. Like, they came up with the craziest ways of playing it. And I think that giving it to other people to play is really important, because you can get really in your own echo chamber where you're like, of course you play it this way. And then somebody else picks it up and does something you never thought of. And you're like, oh, totally. Haven't explored everything.
Is that similar for you all? Discovering other things through working with other people or letting other people play? Or?
Well, I guess, most of the things I've built, I've built for myself. And I do spend quite a bit of time in designing it. And you're right, you do get to a point where you want to just keep adding stuff. And I was doing that at first. So I didn't have all the three knobs at first. I thought I was done with just one knob. And then I was like, oh, actually it'd be great to change something else and then something else. And then I thought about adding this thing last minute. And I made it so I could change it with something else. So to me, when I was done with this, in the back of my mind, I keep thinking, oh, I'm not actually done. But I'm taking a break from working on it and instead performing with it. Yeah. So, yeah.
Well, our session is over, but these conversations are certainly not. As Dennis says, Loop is all about the chat that we have after. And I hope to kind of follow up with all three of you on my website, because I have even more questions about how these things work and how you all play, in other contexts. But thanks for an inspiring session. Let's have a hand for our three artists.